thank you for being here. We have the pleasure of hosting Deniz Gunceler from Microsoft Research today. Deniz received his PhD in theoretical physics from Cornell, focusing on density functional theory of liquids, which I have no idea what this is. He spent 8 years at Amazon Alexa as a senior applied scientist and then as applied science manager working on AI-powered voice technologies. And in 2023, he joined Microsoft Research as a principal research engineering manager in the AI for Science initiative, where he applies advanced AI methods to scientific problems at the intersection of physics and computation, which sounds super exciting. Deniz Hocam, looking forward to your talk. Thank you again for accepting our invitation. Stage is yours.
Thanks a lot for making the invitation. It's a pleasure to be here. I was in Koç University not that long ago, back last August. Nanotere was hosted in Koç University, so I was also a speaker there. So it's very nice to be back, even though this time it is virtual. Today's talk is going to be a little bit different than maybe what you're used to, because I'm originally a theoretical physicist and I did my PhD in theoretical physics as well. I did a little bit of a detour through pure machine learning and language modeling, but 2 years ago I came back to what I find to be a fairly interesting intersection of physics, chemistry, biology, and also machine learning and AI. So the title of my talk today is called Transformation of Natural Sciences through Large-Scale AI and Machine Learning. And I'll walk through a couple of examples of the stuff that's currently going in our lab. So just a very rough sketch of what I have in mind for today. First, I'll do a very brief introduction of the work happening in MSR AI for science, just a bird's eye overview. Then I'll give one particular example on generative models for materials discovery and design. And then I'll go into the last part of my presentation today, which is a little bit speculative. And this is on the bigger picture. And I want to talk a little bit about why I think this is a very exciting time to be working at the intersection of machine learning and natural sciences. By natural sciences, I mean physics, biology, and chemistry. But for the large part, what I'll be talking about today involves chemistry and material science. Microsoft Research AI for Science is a new lab, a new global lab that Microsoft formed back in 2022. I joined AI for Science a year later, almost 2 years ago. My 2-year anniversary was last week. And this is a global lab, meaning that we have lab members in almost every country across the globe and almost in every time zone. Our headquarters are in Cambridge, UK, not Cambridge, Boston. Cambridge, UK, with satellite offices in Redmond, Berlin, Beijing, Shanghai, and Amsterdam, where I'm also based. And just last year, we hired 2 contract software engineers working remotely out of Istanbul. So those are Mert and Emilcan. Unfortunately, by the time I made this slide, Emilcan still hadn't sent me a picture. So that's why you see a generic box instead of his profile photo. So we're primarily a European centered lab, but we have members in almost every time zone. We're also a fairly diverse we also come from fairly diverse set of backgrounds. We have machine learning experts here, language modeling experts, chemists, biologists, material scientists, physicists, mathematicians. It's not just spanning a wide range of time zones, it's also spanning a wide range of backgrounds and the disciplines as well. And the hope of this new lab is to revolutionize the scientific discovery process through the application of state-of-the-art machine learning and large data sets. So I was thinking about how to best represent the work we do at AI for Science, and then I realized the best way to showcase what we're doing is to give a couple of examples of recent open source packages and papers that have been published from AI for Science. We also do work that's not open source and exclusive to internal and external customers, but for obvious reasons, those are not the ones I can talk about in public labs. So today I'll be focusing mostly on the open source work coming out of our lab. Here is mm, a selection of some of the recent work that has happened in the last 2 years. My team have been involved in several, but not all of these. I'll just walk through this list just to give you a sense of the kind of work that happens in AI for Science before jumping into specifics about how we use generative models in materials discovery. So the first work is something that came out about 2 years ago. That's TamGen, and this is a generative model for generating drug molecule candidates for targeted applications. So primarily targeting specific binding sites. This is a model that can generate candidates for the clinical study. Next, we have Aurora, which was published last year, which was open source last year, but published this year. This is one of the largest at the moment foundation models for atmospheric and climate modeling. As you see, we do cover a very wide range of disciplines as well, everything from materials to drug discovery, all the way to weather climate modeling. So next is AI2 BMD. This is again a relatively recent emulator that we've open source coming out of the Shanghai team, and this is using machine learning to accelerate molecular dynamics simulations specifically for proteins, again targeting mainly pharmaceutical applications. Then we have MatterGen and MatterSim, which are the two models that I will be talking in more detail about today. These are essentially again using using machine learning to emulate and generate candidate materials. Then we have the biomolecular emulator, which was just open source, and the model is also now available on Azure Foundry as of yesterday. This is again a machine learning model that accelerates the dynamics of proteins, especially protein drug interactions. And lastly, we have Nature LM, which is a language model fine-tuned on scientific data, targeting applications as a co-scientist or a helper for scientists working on new ideas. Nature LM papers out, the model's not yet open source, but it's also in the pipelines. And finally, there is a new open source model coming from my team in June. I was hoping we would have gotten it out by this talk so I could talk about it, but unfortunately it needs another month or two. But so I'm anticipating mid to late June. We will also open source this model as well. So this is a rough outline of the work that's happening in AI for Science. As you see, it does span a wide range of domains and application areas, but the underlying principle is the same. We're using state-of-the-art machine learning tools, coupling them with large data sets, and then using this to solve problems in the natural and the physical sciences, motivated also partially by application areas in pharmaceutical industry, in materials discovery, and so on and so forth. Just yesterday in the Microsoft Build conference, for example, there was an announcement that Microsoft is pairing up with several major pharmaceutical companies. This is an example of the kind of work, uh, kind of um, work our work enables. So, with that very rough outline, now I'm going to jump into a specific example about generative models for materials design and discovery. But before I talk about that, I want to do a little bit about the kind of terminology that we use when we talk about these models. And the terminology we use a lot is emulators and generators. An emulator is basically something uh, that uses machine learning to uh, to uh, to accelerate a known physical law or a known physical equation. An example to this is that I give you a crystal with a known crystal structure, and then you want to predict its properties. Say you want to predict the thermal properties, the electrical properties, the band gap, the hardness, the stiffness, the bulk modulus, conductivity, so on and so forth. This can be done, of course, using first principles simulations, using fundamental physics, like, for example, density functional theory. However, these simulations are rather expensive. So what we do is we build emulators that emulate the physics underneath. This is done by generating synthetic data from these equations and then training a machine learning a machine learning model on this data, so that this machine learning model learns to accelerate the physics and get us the results either faster or through better scaling laws. A lot of these fundamental physical laws, they have terrible scaling. For example, density functional theory is n to the 4 in the number of particles that you have in the system. So if you double your system size, the calculation becomes 16 times more expensive. So these calculations are very accurate, but usually prohibitively expensive, or they scale really bad, and we use machine learning to basically go around these scaling laws. The second kind of model, and Matterson, the GitHub link is added here, is an example to this. You basically give it a crystal structure, it then emulates the physics to return the properties of that crystal. The second kind of model, and that's the kind that I will talk about next, is a generative model. These are inspired largely by the success that language models and text, image, and video generation models have achieved in the past couple of years. And the idea is to flip this around. Rather than giving the model a crystal and asking it to predict the properties, we have a number of target properties in mind. Say we want a material with a certain level of thermal conductivity, and then we want the model to give us candidate materials who might have these properties. Very similar to how you might generate text, image, or video, these days. And one example there is this MatterGen model linked here. Just for reference, I've added the links to Mattersim and MatterGen here. And just for fairness, I've also added the link to GNOME from Google DeepMind as well, for a couple of reasons. One, DeepMind published this paper a couple of months before we did. So for fairness reasons, I thought it would be good to also mention it here as well, but also to demonstrate that you're not unique in this regard. There are multiple teams working around similar ideas. With that said, I'm going to change gears a little bit and talk about generative models. And first of all, image generation models. Yeah, I know that this audience has probably quite a lot of people who are experts in machine learning. So this part might be a little bit boring or very simple to you, but just to make sure everybody is on the same page, I just want to talk about this a little bit as well. So apologies in advance if this stuff is extremely easy for you. But so one of my pet hobbies is image generation through models like Stable Diffusion. I also have a small server at home with a couple of nice graphics cards. I also like fine tuning my own models. And having lived abroad for more than 15 years, when I do get homesick, I download pictures of Istanbul and then fine tune these models, these pictures. So one example picture I have on the left-hand side is a picture of the Bosphorus generated from a fine-tuned version of the Stable Diffusion Excel model. This is a model with about 3.5 billion parameters, almost 2.6 billion on the UNet, and slightly less than a billion parameters on the text encoder. On if 16 bits floating point precision, this model is roughly 6.5 gigabytes large. And when you do inference with 1K image resolution, this model uses about 15 gigabytes of peak memory, which, by the way, is the just at the limit of what my laptop can handle. I have a mid-range laptop from 5 years ago, and it's just barely able to handle image generation with this kind of model, which, by the way, is fairly impressive. If you had told me 10 years ago that I could just write a bunch of in text and then get an image that looks very much like that text, I would have probably called you crazy and said that that future was 20, 30, 50 years away. And it's fairly impressive how far these models have come. And the way these models work conceptually, they're relatively simple. How you train these models is that you take a bunch of image to text pairs, or sometimes even just images without accompanying text. And then you add noise to these images. So that's what's depicted on the slide. On the left-hand side, we have a clear image with no noise. As you move from left to right, you see more and more noise is added to the image. At the center, you can still make out what the picture is about, but it's clearly very noisy. And when you go all the way to the right-hand side, at that point, you can just barely make out these silhouettes. The noise is almost completely overwhelmed the image. Once you have this data with noise added to it, what you do is you now train a model that denoises the image. So that basically takes a noisy image, calculates the gradient that removes the noise, and then you solve a differential equation that successfully removes noise from the image with guidance from the text you provide. And then that's how you go from pure noise all the way to clear image. So you generate data through this noise addition process, and then you train a model that goes in the reverse direction. And then once you have this model during inference, you begin from just pure noise, and then this model can turn pure noise into a clear image. Now, of course, this is a simplification of what really happens. These models have gotten very sophisticated over the years. For example, that there is a class of models called consistency models that jumps over this denoising the differential equation entirely and goes from pure noise to clear image, usually in a very small number of steps. So the idea I'm presenting to you here is an oversimplification of what really happens, but at the same time, I think it's a good mental model of how these models work. Now, the question is, what does this have to do anything with materials? So as I said, like our goal was to create a model that can give me a material with the desired properties. And the idea is, can't we do something very similar? If we can add noise to images and then train a model that learns to denoise an image, why can't we take crystals, real materials, add noise to them, and then train a model that learns to denoise a noisy material? So this is if we followed exactly the same process. We start from table materials, real crystals that are known to exist in nature. And then we corrupt these by adding noise. We move atoms, we remove atoms, we change the symmetry of the crystal, we twist the unit cell. And by the end of this process, we just end with a random blob of atoms. And then we do the same thing. We train a model that learns to denoise this random blob of atoms into a material that can actually exist in nature, a material that's stable. Now, of course, we want these generated materials, first of all, to be novel. We don't want to get the same materials that we trained the model with, because then that's just a very expensive database. We don't need a database of materials. We need a model that can generate novel materials that we haven't seen before by looking at materials in the database. The next thing is stable. We want these materials to be under specified conditions, to be stable, meaning that some experimentalists can go to the lab and synthesize them. And this stability is usually defined as, if you look at each atom in the crystal, the forces on these atoms should be zero. And finally, we want these materials to have the targeted properties. Again, coming back to the image generation example, when I generate an image, I want the image to look like the text I provided. When I say I want a picture of the Bosphorus in Istanbul, I want to get a picture of the Bosphorus in Istanbul. If I get the canals of Amsterdam, even if it's a beautiful image, that has failed. The model has failed to do the task that we expected it to. And here as well, if we say we want to get a model with a certain magnetic properties, we should get the model with those magnetic properties. And here are some of the examples, novel materials that has been generated with MatterGen. So there are 6 crystal structures on the slide. The 2 on the left, those have been targeted to have a very large amount of magnetization. The 2 in the center, there we targeted optical properties. These materials have been generated from the model to have a band gap of almost 3 electron volts. And it doesn't get it exactly right, but it gets it mostly right. And the ones on the right-hand side, the 2 on the right, those have been targeted to have a bulk modulus of 400 gigapascals, and it gets them fairly good. One of them has a bulk modulus of 407, the other one has a bulk modulus of 398. Just an example of the kind of materials that we are able to generate with this kind of model. Materials that are novel, new, materials that are stable, meaning that they should be, it should be possible to synthesize them, and finally materials that have or approximately have the desired properties that we want to have. And this model, and also multiple variants of this, is available in GitHub. So you can download it and then run it. So now I want to talk a little bit about why we're doing this. Like, what's the motivation behind having a model that can generate candidate materials? And this is one example. So magnetic materials are extremely important in today's electronic technology. So if you buy many of our household electronic devices like laptops, smartphones, cars, so on and so forth, these would have the different kinds of magnetic or magnetizable materials in them. So this is a fairly big industry. But a lot of these materials are actually quite difficult to find, meaning that there are either very few suppliers of these materials, or they're expensive, or the supply chain comes from parts of the world where there is uncertainty. This is quantified in something called an Herfindahl-Hirschman index, the HHI. This number basically quantifies supply chain risk. If you as a company or a country are depending on a specific material. This number gives you an estimate of how much risk involved in getting this material. So, for example, when there are multiple suppliers of this material around the world, this number goes down. If there's a single supplier, then this number, of course, goes up. If the single supplier comes from part of the world that's quite unstable and unpredictable, this number goes up even further. So we want to create materials that have magnetic properties, but also low HHI index so that they don't pose a supply chain risk. And this is what is shown on the plot on the left-hand side. The y-axis of this plot is the HHI score. High means bad, low means good. The x-axis is the magnetic density of this material. The green, the mint green dots are materials in our database, which we've used for training. And the X, the black X, is the target, which is low HHR score and high magnetic density. Oops, sorry. And the purple and blue dots are the new materials that have been generated by Mattergen, aiming for this target property. So we are able to generate material candidates that have low HHI index but high magnetization that are not in the training set. So this is the motivation for this kind of work, finding materials that have targeted properties that can have economic value. And just an example, this work was actually highlighted by our CEO in the last World Economic Forum a few months ago. And given the economic value this could potentially bring, you can probably guess why. Now, I want to go into the next part of my talk, which is, as I said, a little bit speculative. And I want to talk about why I am excited about this and why it's a very good time now to be at the intersection of machine learning or AI and natural sciences. Just a couple of examples that I want to provide. So what I did a few months ago is I went on Hugging Face, I went on the local Llama subreddit and also to the Llama CPP project page. And then I download and I just looked up what are the most popular open source models right now. And I just prepared this slide on their size in the number of parameters. So we have small language models like, for example, Qwen3, which was just released, ranging all the way from almost 2 billion parameters all the way to 14 billion parameters. There's also 5.4 coming from Microsoft research as well, which also have 14 billion parameters. And there are also much larger language models like DeepSeek, which is more than 600 billion parameters. There's a large version of Qwen, which is more than 200 billion parameters, and Llama 4 has almost 400 billion parameters. And if you go to multimodal language models, they also range from small all the way from 2 billion or even 1 billion parameters, all the way to almost 80 billion parameters. Likewise, for image generation, there are popular models out there that range from 1 billion to 12 billion parameters. Lux one, which is probably the best image generation model these days that was released like last year, that is 12 billion parameters. And if you also look at the video generation models, they're also kind of in the same ballpark range. Now, you might ask why I'm going over all of these model sizes. The reason is that I want to compare these model sizes to the sizes of these models that we're currently using in natural sciences. So I've included MatterSim here, which has multiple open source versions. And you're not seeing this wrong. The part that highlighted in red, it says 1 million parameters, not billion, 1 million parameters. And the larger version of this model that we released has 5 million parameters. As you can see, these models are 3 orders of magnitude on average, smaller than the state-of-the-art language models or state-of-the-art open source AI models that are popular these days. So as you see, we still have a long way to go. Likewise, on the data side, I want to compare the data set sizes as well. So one of the largest materials data sets, one of the largest open source data sets is OMAT 24 from Meta. This has about just a little bit more than 100 million DFT calculations in data set, and the whole data set, if you try to download it from Hugging Face, is approximately 185 gigabytes in size. Now, compare that with Common Crawl, which is one of the main data sets that is used to train large language models these days. This is growing at a rate of approximately 400 terabytes a month, which is from April of last year, and approximately 3 billion pages, not tokens, not words, 3 billion pages per month. And the total dataset size is now estimated to be more than 10 petabytes in size. The other dataset I want to compare against is Lion 5P, which is one of the largest datasets that have pairs of images and text. The Lion 5P is used in tasks like, for example, image generation. This SD Excel fine-tune I showed you earlier was originally pre-trained on this Lion 5P dataset. This has 5.85 billion, not million, but billion image to text pairs, and the whole data set is larger than 200 terabytes. Now, not only are the models we're using on natural science much smaller, our data sets are also much smaller as well. So again, by approximately 3 to 4 orders of magnitude. And finally, I want to compare apples to apples. And this is now, I want to compare language modeling datasets. So this screenshot is taken from the Nature LM paper that just came out a few months ago from our lab. And it's showing how many billion tokens that we use to train the Nature LM. As I was saying earlier, Nature LM is a language model from Microsoft Research, AI for Science, that is aiming to be like a co-scientist. It's a language model that can understand science, that can reason with science, and then it can interact with the different scientific modalities. We've trained this approximately on less than 13 billion tokens. Now, compare that with the training dataset size for example, DeepSeek V3, which has been trained on almost 15, not quite, but almost 15 trillion tokens. Again, just on the pure dataset size, we have a huge way to go. The datasets used in natural sciences are significantly smaller than what we're using in state-of-the-art machine learning these days. And this is exactly why I'm excited about being at the intersection of the natural sciences and machine learning these days, because what the results we're getting with models that are 3 orders of magnitude smaller than what's possible right now is already showing great and very promising results. Imagine what we can accomplish once these models reach the boundaries of what we can achieve. So I feel like this whole field is right before ChatGPT came into the scene and exploded language modeling. Before 2022, before ChatGPT it became a hit, language modeling it did of course exist, and it had been in existence for a very long time. But that was the moment that when things really became exponential and they exploded. Just seeing the results we're getting with models 3 or 4 orders of magnitude smaller than what our technology can achieve right now gives me the hope that once we scale up to the model sizes and the dataset sizes, and that, for example, are now typical in language modeling, imagine the results that we will be able to get at that point. And what's even more encouraging is we don't need new hardware, for example, to reach here. We don't need new machine learning algorithms to reach here. We just need to catch up with the state of the art. We already know that models that have hundreds of billions of parameters are possible with current technology, with current GPUs and clusters and cloud technology. It's just that natural sciences haven't reached there. And seeing the results we're seeing right now with the models we have that are incomparably smaller gives me the feeling that natural sciences, so physics, chemistry, biology, are right at the cusp of their chat GPT-like moment. So, and this comes back to my original premise, why I'm excited about this and why I'm very excited to be working at the intersection of AI and natural sciences. The question is, are natural sciences doing large-scale AI at the moment? And the answer is no. I mean, we're climbing up the ladder. We're building larger models. We're building larger data sets. But the models and the data sets are nowhere as large as what's possible with today's technology. And imagine if you're getting these extremely promising results right now, imagine what we can accomplish with 3 orders of magnitude more data, 3 orders of magnitude more parameters in the model. And just to quantify this a little bit, I took a screenshot from the Matterson paper showing the impact of scaling up. On this plot, the x-axis is the data size, the number of data points we use to train the model. The y-axis is the absolute error in the emulation, so the comparison between what physics tells us and what AI tells us. These lines show different data sets that Matterson was evaluated on. One important thing to note is that when we increase data set size, we also scale up the model size as well. It usually doesn't make too much sense to just increase one of the two. If you have larger data, you can also train a larger model. And if you don't have more data, training a larger model doesn't usually make too much sense. So, and what's also very important to note is that both axes are logarithmic axes. So this is a log-log plot. So if you move even one tick, that's basically 1 order of magnitude. And as you can see, as you make these data sets larger and the models larger, the errors are going down. And these models have not yet saturated. So we know by extrapolating this curve, what we think we can accomplish in a few years. And we're still very far away from saturating these models, from saturating these ideas with data. And it's just a matter of scaling up at this moment. So I think I'm almost out of time. There's maybe a couple of more minutes to go, I think. So I would like to just wrap up with a couple of closing thoughts. As I said, I wanted the second half of this talk to be a little bit speculative, not so much of what we're doing right now, but what we can do in the future, because I think that's the more exciting part. I think the one message I want to leave with today is physical sciences have just begun to scratch the surface of what's possible with large-scale machine learning. And the models and data sets are larger than they were 5 years ago or 10 years ago, but they're still nowhere as large as what's possible with today's hardware. So the models we have, the small models we have, already show great promise, and we're looking very much forward to scaling up these models. Just maybe one asterisk to add there is, and this is maybe just one negative bit to add on this positive message, is a lot of our training data for these models comes from something called density functional theory. This is one of the most successful simulation methods that is used to approximate Schrodinger's equation, which is one of the most fundamental equations in physics. By approximating Schrodinger's equation, we can generate a physical training data to train machine learning models on. And we're slowly approaching the point where this approximation is becoming the limit. So because the model can be only as good as the data it's trained on, and we're approaching the point where the primary technique that's used to generate data is saturating. So that's maybe one negative message that I want to conclude with, because you might ask if it's possible to have just larger models and larger data sets. Why don't you? What's stopping you from having, like, realizing this vision? It's primarily this, that just generating data in a cheap, fast way, you're beginning to see the limits of this. And one of the challenges here is going to be, how can we either generate or find more data to scale these models up to the next level? So with that said, I think I'm 2 minutes early, if I'm not mistaken. So yeah, I wanted to say thanks a lot for listening to me, and I'll take any questions if you have any.